And so, you know, if this information comes from the nameplate of a three-phase induction motor, it tells us 500 horsepower. And so remember that, you know, if that's on the nameplate, that's a mechanical power outrating. 2300 volts, you know, big motor, right? 500 horsepower, 2300 volts is the line voltage at the input. 130 amps then will be the line current, of course, at the input. And that's the full load current, of course. And then 1730 RPMs, of course, is the running speed in. And so, approximate values of lock rotor current and no load current. I remember I told you that that would come up somewhere. And so that's two numbers that you just got to remember. And so we said that I no load is approximately equal to 30% of I full load. And I full load, of course, is that rated current that we're giving up there from the nameplate. And so, therefore, we can say that the no load current is approximately equal to 0.3 multiplied by 130 amps, and that gives us 39 amps. Now, the lock rotor current, which we normally just call ILR, is approximately equal to 5 to 6 times, that's our assumption, right? The no load, the full load current. So, I'll just go with 6 because then that gives you approximate of the maximum value that you can expect. So ILR then is approximately equal to 6 times the 130 amps. And that gives us 780 amps. And so that's a lot of current. Now, and so, you know, one of the things that you might want to know that current for is so that you can help size the power supply. And so this says the approximate apparent power drawn under lock rotor conditions. And so S3 phase. And so remember that we talked about the fact that, you know, there's probably some other information on the nameplate with respect to how much apparent power it wants under lock rotor conditions with respect to a code letter, right? And so that helps you size the power supply too, of course. And so we'll say then that S3 phase under lock rotor condition is approximately equal to √3 times V line multiplied by the lock rotor current. And so again, you know, this is a huge number because that's a really high current and of course a very high voltage. So √3 multiplied by 2300 volts and the 780 amps. And that gives us a value of like 3,107,000 volt amps, which we would round to, if we're using three significant digits, 3.11 MVA, right, megavolt amps. And so, you know, it's important to have some idea, I think, of that value, because your power supply got to be capable then of a high value of power and current for startup. And remember what we said about lock rotor current, right? You know, sometimes 5 to 6 times is practical to expect it to flow. The motor suggests that a lot higher than that, but the fact that it starts immediately means that is limited. But if we got reason to believe there's going to be 780 amps at 3.11 MVA, then we got to make sure our power supply is strong enough to take that jolt or boost during startup, right? And so it's important to consider them values when you're talking about starting circuits. And you know, in that case, you probably want to think about not starting that under load, starting with reduced voltage methods and the stuff that we talked about for the DC machines. That kind of applies here too. Now, the nominal rating of this motor expressed in kilowatts. And so when we talk about the nominal rating, of course, nominal and rating kind of means the same thing anyway. And so what we're saying is that the power out rating of that motor is 500 horsepower. And they just wants us to write that in terms of kilowatts. And so in order to do that, we multiply by and so remember now, they said kilowatts, and so we can go with 746 watts per horsepower, or we can write that as 0.746 kilowatts per horsepower. And of course, horsepower cancels. And the nominal or rating of the motor, written in terms of kilowatts, then 500 times 0.746 gives us 373 kilowatts. Okay, part D is the approximate full load torque, and you'll notice there that I did not ask for torque developed because we don't know it. We got no information about losses here or a power flow diagram or anything. So really it's T out that we're calculating, not torque developed at all. And so we'll say then that that is 9.55 times P out, because that's the only number we got, right? So it's torque output. And so there I'll just call it full load torque. If we could find PMI and have a value for torque developed, and I would specifically ask for torque developed, right? Okay, so now we have then 9.55 multiplied by the 373 kilowatts for P out, and divide that by the running speed, which was off the nameplate, 1730 RPMs. And if you calculate that number, you come up with 2059, and that's the 9.55 times 373 over 1730. And so in actual fact, yeah, Newton meters. So that's the 9.55 times 373,000 divided by 1730. And so we could write that as 2.06 kilo Newton meters. And that is torque out. No, 2059. Okay, so